Imagine holding a brand new deck of playing cards. Every card is perfectly sorted by suit and number. Now, toss them high into the air and watch them scatter across the floor. If you were to gather up that messy pile, throw it up into the air a second time, and hope they all land back in that original perfect order, what do you think the odds are? You already know the answer. It is virtually zero. To get them perfectly sorted again, you have to sit down and physically do the work of organizing them. They will never organize themselves. This sliding scale of disorder is what scientists call entropy. It's a way to measure just how far a system has drifted from a state of perfect order. The universe favors this messiness for a very simple reason. There is only one way for a deck of cards to be in perfect order, but there are billions of ways for it to be a jumbled pile. Chaos is simply much more likely to happen. While cards are a great way to see the math, this principle buffers every physical object in our world. You can see it in action simply by watching how heat moves. If you leave a steaming cup of hot tea on a table in a cool room, that heat will always escape the cup and spread out into the air until the room and the tea are the exact same temperature. You will never sit in that room and watch the surrounding air suddenly freeze so that your lukewarm tea can become boiling hot again. The energy has spread out, and it will not gather itself back together on its own. This animation shows what happens on a microscopic level when an ice cube absorbs heat from a warm room. The rigid, tightly packed structure of the water molecules breaks down, becoming a loose, moving liquid. The energy in the room has scattered. Just like our deck of cards, the structure has moved from highly organized to highly disorganized, showing us that natural processes only run in one direction. For centuries, inventors tried to find a way around this one-way street. The dream was to capture highly organized energy and build a machine that could run forever. Looking at this early steam locomotive, you can see our attempt to cage that energy. We burned coal to create intense heat inside heavy boilers to force the wheels to turn. As we built massive factory presses, like the one in this photograph, the machinery grew incredibly complex, using thousands of moving parts to bend that energy to our will. This image shows the inside of an engine, specifically the red combustion chambers and sliding pistons. To make them move, the engine burns fuel. The tightly packed energy inside violently expands, scattering much like our deck of cards thrown into the wind. The engine isn't destroying the energy. It just takes something neat and orderly, like fuel, and forces it into a messy, permanent state of disorder. You can actually feel this disorder in the real world. When an engine runs, the hood of the car gets hot, radiating waste heat outward. This diagram illustrates the second law of thermodynamics. In any isolated system, total disorder only goes up. Notice how the concentrated heat drifts into the surrounding area. Once diluted, it cannot be gathered back to do useful work. The energy remains, but is completely degraded. Because every energy transfer loses a little bit of itself as unusable, spreading heat, a machine running forever without new fuel is completely impossible. You can think of waste heat as a tax collected by the universe. Every time you try to do something useful, the universe takes a cut, ensuring that absolute perfection can never be maintained. Now take that exact same rule and look up at the night sky. Looking at this photograph of distant galaxies, you can think of every point of light as a massive engine. Stars are furiously burning through highly concentrated pockets of energy. See the bright center of this galaxy radiating light into the void? It is bound by the exact same tax as a car engine. It is constantly bleeding heat into the cold vacuum of space. Every single time a star shines or a black hole spins, the universe is shuffling its deck. It is taking highly organized energy and turning it into ambient, unusable background heat. The entire cosmos is acting like one colossal, slowly leaking machine, steadily ticking down as its energy drifts further and further apart. Fast forward trillions of years, and this universal shuffling reaches its absolute limit. The last stars will eventually burn out and fade to black. All the concentrated energy will be totally dispersed. With the heat spread perfectly evenly, there will be no hot and cold spots left, and without temperature differences, nothing can move, and no natural processes can happen. Scientists have a name for this ultimate state, where the messiness is at its maximum: heat death. It's the final equilibrium where everything reaches the same lukewarm temperature. Fortunately, you don't need to worry. We have trillions of years of warmth and starlight left before our cosmic coffee cools down. But it does put our daily lives into a comforting perspective. Think about a messy bedroom or a spilled drink. When things inevitably become disorganized, it is not a personal failure. You are just experiencing the most powerful, unbreakable law of physics at work.